Thanks. Yeah, good morning. Great to be here. I will talk about the challenges in embedded testing. And when I mean embedded, I mean deeply embedded system. I think Stefan called it tiny devices this morning in his opening speech. What are these challenges? To understand that, let me allow to start with a bit of history to give you a mental model what I mean. I'm coming from Lübeck. Lübeck is located next to the Baltic Sea in the north, next to Hamburg, and the city got very rich during the Middle Ages because of trading. And at some point, the city council decided that they need a gate to defend themselves, protect their wealth. So they built this, it's called Holstentor in German. During that time, it was in 1464, new weapons came up, cannons. So they had to build it with really thick walls. I think the diameter of the walls is about 3 meters, 3.5 meters. So very heavy, the whole building. Who of you has been to Lübeck? Only a few. It's a lovely town. Go there for a visit. For those of you who haven't been there, there's a lot of water next to the city center. So everywhere is very swampy soil. Swampy soil and a heavy building. The building has a very bad foundation, so it's tilting. The whole building is tilting. And I think about 150 years ago, it got so dangerous that the city council almost decided to demolish the whole building. Instead, they fixed this, and they fixed it again, and the Nazis, ironically, managed to permanently secure it. Like, you can go there today and safely make a selfie. Why I am telling this to you? This building is not collapsing, despite its tiltness. So why it's not collapsing? Because they managed to build it only with a height of 20 meters. You can assume that they were wise enough, the people in the Middle Ages, to know how far they can build, how tall they can build. And this is a thing, from my perspective, in embedded, we don't manage to do this right. We build too high. What do I mean here? If you think about an embedded system, you have the hardware as a foundation, the silicon, the chip, the microcontroller. In this case, for example, an STM32 chip. On top of that, you have the register definitions. So typically, the chip vendor provides some definitions, and you can use them, for example, to access a timer or to access a GPIO. If you have a good software, you will not access this directly from the application, but instead you will use a driver layer. So, for example, the driver might provide something like this, a function to create a pulse on some pin with a specific length. And then the application can use it. If it would look like this, there would no need to be here today. I think it's much more looking like that. Much more unstable, In recent years, there were a lot of new requirements for the application. Think about stuff like connectivity, IoT, even machine learning, a lot of new functionality that needs to be implemented in the application. And embedded engineers did it. So the driver layer here, the foundation, is, from my perspective, not stable right now. We have problems with the drivers. And I will explain this conjecture with a few challenges I think are preventing this layer from being solid. So that's the first part of my talk. I will talk about these challenges that face us in drivers. And then I will propose open loop tests that might be an alternative to write better drivers. So let's start with the analysis. To talk about the same thing, I will use this example embedded system. It's drive control. So it might be a system, a little box, this blue box here, it might be a system in your car that tries to control an engine, a drive, to reach a specific speed. You can assume that it's its target speed via CAN, and then it uses some power electronics to create this output for the drive. And of course, the microcontroller is not directly powering the drive, but instead it's talking to the power electronics, for example, by creating these pulses. Yeah, the longer the pulse, the more power the electronics will give to the external drive. So you already see we need a few drivers to make this work. We need to read the signal from the speed sensor. We need to create these pulses. We need to talk to the CAN bus. And maybe we also need to access some I2C bus for a temperature sensor, which is on the board. Okay, so we need to write drivers. How do we do that? And what are the challenges? The first challenge is the silicon itself. Modern chips are getting really, really complicated. The example I will later show you is based on an STM32. The reference manual here is around 3,000 pages long. And it's not like that there's a lot of blah, blah, but potentially all of the information in there is relevant. You cannot just skim it and program something because there's a lot of interdependency between the peripherals. And for example, if you look at the timer code, these are several sections in the manual. I wrote it down. It's 431 pages in the reference manual telling you how you need to, what you need to do to measure times. So really complicated. That means to have an overview of your hardware is really complicated as well, which means writing the driver is by itself complicated. Okay? The next challenge, that's the first challenge. We cannot do anything about it because the market demands these chips. They are great, but it's a given, yeah? The second challenge is a little bit different. It's about the software. Typically, the chip vendors deliver you some driver code, some example driver code, and you can use that in your projects. If that would work, we, as a developer, we would not need to write any drivers because they are delivered by the chip vendor and supposedly they would test it in a good way. That's not true. And it's not true for several reasons. I think the most important reason is that embedded systems are so different. Each project is unique. You have different requirements for each project, so you need different drivers. The fascinating thing about writing embedded code is to combine the peripherals in an efficient way to write a good piece of code and software. So there is no standard set of drivers. Instead, you will most probably you will need to write your own drivers or adapt the drivers. So I know from practice that a lot of people are just taking these examples and adapting them for their purpose. Which also means we need to test them somehow. The third challenge is about testing. And from my experience, I worked for several years in a safety-related industrial context. And the approach there was you start a new embedded development project. The developers start programming, maybe get some early hardware. And at some point, some system functionality is finished, and the developers ship it or give it to the test department. So a different department that then starts doing system tests. And I think this approach is pretty common across different industries. And there are several problems to this approach. System testing is intended to check the whole system. And the important thing is they test on the outer bounds of the system. So in this case, they will test on this, and this interface here. To do that, they need to attach some hardware. Maybe they attach a real motor. Maybe they attach a simulation. But importantly, they need to simulate the whole environment. Because if the embedded system is putting out some power here, it expects that the engine starts rotating and then that the speed sensor signal is also adapting here. And with this kind of testing, you can check requirements like if a speed of 100 RPM is transmitted by a CAN, the system must have reached the speed between 98 and 102 rounds per minute within 2 seconds. That's a system requirement, and you can test it with this approach. What you cannot test is the internal states of the system. So think about this, some test is failing. If this test is failing, you don't know if there's a problem in the driver or in my circuit, or maybe also in my test simulation. There are different things where something can go wrong. And that's why this process is limited. You will never know with this process that your driver is working in all circumstances. You can only test it indirectly. Also, of course, it's difficult to automate. It's very expensive. It takes time, and in practice, this means the project is almost finished when the test department gets their test stand up. And it obviously has problems. Is this use case clear? Or any questions here? Okay, great. So, how can we do better? How can we test these drivers? Yeah. If we look at the structure of the system test, we might get an insight. If you think about it, the system test does 2 different things. It's influencing our target system, for example, by sending the scan message. And it's also simulating the environment. And to do the simulation, it needs to continuously measure the outputs. And depending on the outputs, it's generating inputs for the system. So we have this closed loop in your system test. It's in all system tests. And closed loop brings us, maybe some of you heard about control theory. Who studied that, had this, knows about control theory? Okay, those of you probably suffered like I did in my studies. Control theory is a difficult and really complex topic. It's also fascinating. You can achieve things like that. There is a pendulum, and the control system holds it up. So the guy is influencing, disturbing it, and the controller continuously measures this angle and modifies or changes the horizontal axis to influence the system and keep it up. And in the end, he stopped it, and it's obviously immediately falling down because it's an unstable system. So great stuff, but you can also easily mess up and get some instability or something. Okay, closed loop is powerful and complex. And if we compare this to our system test, it's basically the same approach. You continuously measure the output, the angle in this case, and then you influence the system. Our system test would measure the energy output and generate a speed signal. Yeah? It's the same structure. Fortunately, in control theory, there's also a much simpler alternative. It's called open loop. And open loop does not measure the output. So you can use it for situations that are not disturbed somehow, where you just know how the system will react. Surprisingly, there are several applications to do that. Think about a water pipe, and you have some valve, and you need to open the valve in an optimal way, so that the water is started in the best way, the flow. You can use that. You know how this physical system will react, so you can design some curve and apply it to the system with an open loop controller. And that's really simple to analyze because this feedback is missing. And we will use this structure to devise an open loop test for our drivers. The important thing is here that we get rid of the feedback loop, and this means we don't have any simulation anymore. Instead of testing the whole system, we focus on the microcontroller. So MCU is microcontroller. That's our device under test now. And our test system just stimulates the inputs of the system. For all embedded systems, these are two inputs. The first, all the pins around it, and then the software running on it. If we influence these two things, stimulate them, we can test all the behavior. Same thing on the outputs. If we are able to observe all the pins on the microcontroller, we can also, and we can read functions, we can access all internal states of the microcontroller. Something totally not possible with system testing. I think I just explained this. Any questions for this structure? Because we will use it now to test the driver. Okay, if there are questions, just interrupt me. What we want to do is test this pulse generation. So only a single component of our overall system. And we want to test requirements like this. If the pulse driver is called with lengths between 50 microseconds and 50 milliseconds, the pulse should be within a tolerance of 1%. That's a requirement, not a system requirement, but a component requirement. And this test, so from a test structure, we will influence the code. We call a function on the microcontroller, the driver, the pulse generation, and observe the output. I will do a live demo for this. I did not introduce myself. I'm a founder of emBO, and we are developing a test system, generic test system. So that's this little device here. If you want to look at it later, we have a booth outside. That's a test system where specific microcontrollers inside. So where there's a PCB inside with a microcontroller. In this box here, the STM32. And the box is able to access all the pins. Yeah, they are wired. And so we have access to all the pins. And what I wired here as well are some logic analyzer outputs. So the test system can basically route out all the microcontroller pins to some logic analyzer connection here so that we can understand a little bit better what is going on in the system. Let's try the demo. I had some network issues here before. Maybe it's working now. Is the font large enough? Should I increase it? Little feedback from the rows behind. It's okay, you can read it? No, okay. Is that fine? Great. Okay. So we have some driver functions. This piece of code here has the function create pulse. And the purpose of the function is to get some payload, some length in as a string. Then the function is parsing this string to get a duration in microseconds. Calculating the ticks, the system needs to rate its timer to reach to get this time. And then pin PB10 is set high. Then the counter here is started. The software waits until the ticks have passed, and then the pin is set to low. Okay, it's not important how it's implemented here. Important is that's a function that should create a pulse of a specific length on our PB10 pin. Okay, and our test system, our goal is now to test this. Yeah, so to check if this driver function actually creates a pulse of our desired length. Okay, check this back. Okay. It's an implementation detail. We use robot framework to control the system. But what's important in this talk, I talk about principles. Yeah, that's just one application of open loop testing. Okay, let's write a test. Let's test that a long 7 millisecond pulse is within 1% tolerance. What we need to do, we need to call this function. And for that, our test system provides a keyword .invoke. We tell him that he should call this function. I think it's what creates, create pulse. And the parameter is 7,000 because 7,000 microseconds is 7 milliseconds. Okay. You see this instruction here. It's .flash firmware. There is a debugger inside. So the system will now go ahead, flash the firmware, the implementation you just saw, and then call this create pulse function. It will only work if the network is working, we will see. And before I do that, I connected a SALAI here, and we wrote out PB10, so we should see the pulse here. Okay, run the test. And what's happening now, it's flashing the firmware. It takes some seconds, and then calling the function. Hopefully. Okay. Okay, so, there are some network issues. That's why it took so long. Anyway, this pulse was created. I'm glad for that. You see here on the SALAI, there's a pulse. And we can zoom inside, and you will not be able to read it. It's 7 point something milliseconds. Okay? So the test system was able to call this driver function. But of course, we want automated test. This is just for developing to connect the SALAI. We want to measure with our test how long this pulse actually is. So for that, we call that endpoint. We provide keywords, and we want to measure something, and we want to measure this pulse, so between rising and falling edge. And we want to do that only on PB10. Both edges should occur on PB10. After the pulse was created, we will read back the result. And we read back the result in microseconds. And maybe we can put it to the terminal here so that we can see it. Let's append here some unit. And then I prepared, our test goal is to check against this 1% tolerance, So min-max values. I wrote a keyword for that, check that within 1% tolerance. It's just doing this assert, doing some simple math. The expected value is 7,000. And the actual value is what's inside this variable. So this variable is really, it's measured here on the system, on the real. There's no simulation involved or something. The chip here is inside, and the test system measures this this pulse. I hope the network is keeping up. Let's see. It actually should take only about 2 or 3 seconds. Okay, it's taking much longer, but it works. What you see on the output is this line here. So that's the time the test system measured. And it's about the same time the SALAI told us of the pulse length, okay? Good, but that's only one point, one testing point. What we want to do is check this for multiple values. So let's just go ahead and duplicate this in a simple way. Check a short pulse. Did we do here? So let's do 600 microseconds. Change this value to 600. And duplicate again to have some very short pulse, maybe 50 microseconds. Okay, that's too much. Okay, and now I go ahead and start all tests in run go. We can start SolAI again. While this test is running, the demo here is for GPIO, which is obviously pretty simple. In the real world, without some test system like that, you would connect your oscilloscope or some logic analyzer and measure this manually. But the system can do much more. So it can actually talk to whole peripheries, like sending CAN frames, talking to the SPI interface, things like that on multiple pins. Okay, the tests are running. We see some results. Okay. The last test failed. The 50 microsecond pulse was actually 52 microseconds, which is not the 1% tolerance. So maybe some of you have an idea what's going wrong in the software here. Any idea why this is not exact timing? Yeah. Yes, the string conversion is in the beginning, but actually that's before we start the timer. So the timer starts after the pin is, so the pin is set here, and the string calculation is before, but yeah, it will take a lot of time. But it should not influence the result, the pulse length. But it's basically the same reasoning. We set the pin here before we start the timer. And obviously there is some delay between these functions here. Yeah? Depending on optimization and everything, it will take time from setting the pin to starting the timer. And again, from calling the timer, polling the timer, and stopping setting the pin low. So it would be much better to use hardware implementation. And a colleague of mine, Jonas, he's also here, he wrote this little snippet here that uses PWM, so some hardware periphery to do that. And in theory, it should be able to make this much more accurate because everything is generated by hardware. I will start this because it takes so long and then explain what I did. I just changed the .flash firmware call. So now there's a different implementation running on the microcontroller. And the interface here, if you take a look, create pulse, it's completely the same. So the interface stays the same. That's why the test can also do the same thing.
Can you do the number with 11 characters?
With what?
11 characters, the number. That's 11 characters.
I think I did not get this. Oh. Whoop.
So can you test it with a number with 11 characters there?
Ah, you wanted the function to crash, yeah?
Yes.
Sure, we can do that. First, let's take a look. So, it worked. Maybe you go to our booth later and we do it together, yeah? Maybe you have some idea in a genuine way to crash it. We are a little bit running out of time. So, if we go ahead to the SolAI, we also see, oh no, I did not start it, okay. Anyway, let's go back to the slides, last slide. Okay, yeah, that's it. So what did we see? I hope we can all agree that for solid embedded systems, we need a good foundation. We need good hardware and we need good drivers, yeah, to make this work. And I reasoned about why drivers are traditionally very hard to test. There's a lot of manual process involved in practice. If you right now go ahead, test it without open loop testing, it's a lot of work. And open loop tests, they provide an alternative to system testing, or an extension to system testing. You can do this as a developer. So while writing your test, you can actually start, while writing your driver, you can start testing it, writing tests against it. So you can do a test-driven development with this approach for your driver, hardware-related code. And because they don't need to simulate the environment, they are really easy to read and compact. Yeah? And that's the reason why developers can do that. There's no much knowledge required to write such an open loop test. Okay, and most importantly, they close a critical gap. They allow these hardware-software integration tests, and my opinion is that this will help us a lot to get to reliable embedded systems. So that's my talk. Thanks for your attention. If you want to try this out, we have several demos for several peripheries. We have a booth in the room next to this one. Come talk to us. Pavel, my colleague, is also here. He is the technical lead, so if you have some very nerdy questions, go ahead and talk to him. Thank you.
Thank you, Daniel. We have time for 2 more questions. Over there.
What sort of device do you use within the module to analyze and interact with the pins on the microcontroller?
So what device we do use?
Yeah.
It's an FPGA. So this allows us to dynamically route to all the pins. So a typical microcontroller, like 144 pins. And this FPGA allows us to access all these pins, for example, for GPIO, and then the next case, test case, configure something different, like using CAN or something, and also route it out to the logic analyzer. Yeah.
Cool.
We have some PCB there on our booth. You might take a look.
Another question.
Hi, thank you for the very nice presentation. The question is, I'm not sure I totally understood how do you, if you want to test several driver functions, like you have many functions that you want to test,
yeah.
How are you actually calling those functions? Do you have some part of an application that is dispatching some messages, or how is this happening? How do you get to call each of the possible functions that you would like to test?
Yeah, so we have some very simple registration mechanism. So with each device, we ship some little sample package, and that's a sample package for some drivers, but most importantly, a little piece of our software. And it basically talks to our test system with some, for example, with UART, and receives the comments which functions to call. And basically, you need to go beforehand, register all the functions you want to call, and then you can do that at runtime.
You need to link your driver code with that software that you mentioned, right?
Sorry?
You need to link the driver code that you want
and
with the software.
Yeah, so thanks for that clarification. For open loop testing in general, you will not test the final firmware, because the final firmware obviously expects the whole environment. So you just take your drivers or the code you want to test and link this with a little library from us to some test binary. And this binary you flash. So yeah, thanks.
Thank you.